Please,
Good.
please prepare your share, your presentation. Oh, it's red. And please start when you are ready. Thank you.
Good afternoon to all of you. First, I would like to thank the organizers of the conference for giving me an opportunity to present a paper in this conference. So myself, Dr. Wajih Ashraf, I'm assistant professor in the Department of Mathematics, Aligarh Muslim University, Aligarh, India. And the title of my paper is on closed varieties of semigroups. So this is all about the closeness of the varieties. So first, I will read out the abstract of the paper, and then I will come to some basic definitions, and then I will tell the background of the paper, that what is the idea of the paper through which we will able to prove out all these things. And the last references had been given. So first I will read out my abstract. So in this paper, we have shown that the varieties of semigroup defined by identities axy is equal to x to the power n ay x, axy equal to x a to the power n y a, axy is equal to y a y to the power n x, axy is equal to x a y a to the power n, axy is equal to y to the power n a y x, and axy equal to x a y x to the power n are closed in itself, where n belongs to set of natural numbers here. See, first I would like to tell what is varieties. See, varieties is the class of semigroups satisfying some identities, certain identities. What is identity? A semigroup identity. Say, for example, in general, U is equal to V. U equal to V is a semigroup identity. It is the equality of two words. For example, XYZ is equal to XY. This is an example of semigroup identity. Or you can say XY equal to YX. This is a commutative identity. So it means here the words are the letters, words formed by the letters, and these letters are the elements of the same group S. So anyway, so in this paper, we have shown that these varieties of semigroups are closed in itself. So first, now I come to basics and definitions. So let U be a subsemigroup of S. We say that U dominates an element D of S if for every semigroup P and for all homomorphisms alpha delta from S to P, and UB alpha is equal to U delta for every U in U implies D alpha is equal to D delta. Now we collect such all elements. We collect such all elements. That is the set of all elements of S dominated by U in S. We call it as dominion of U in S, and we represent it as dom US. Correct? So dom US is what? A very important fact is that dom US is what? Dom US is a subsemigroup of S. And it contains U. So situation is what? This is U, this is dominion U in S, and dominion US is contained by S. So U is contained by dominion dom US, and dom US is contained by S. Now, very important definition is definition of closeness. A semigroup U is called closed in S if dominion US is equal to U. That is, U is contained in dominion U in S. When U and dominion both become equal to each other, we say that U is closed in S. That is, U is closed in containing semigroup S. So this is the definition of closeness of a semigroup. Now I come to the definition of absolutely closeness. See, a semigroup is called absolutely closed if it is closed in every containing semigroup S. For example, a semigroup is U is there, and there are 10 semigroups S1, S2, S3 dots on S10, and all S1, S10 semigroups contains U. So if U is closed in all these 10 semigroups, U is closed in S1, U is closed in S2, U is closed in S10, then we say that U is absolutely closed. So these are some very basic definitions which we should know for this paper: closeness and absolutely closeness. Now I come to a very important theorem, that is Isbell's exact theorem. Isbell's exact theorem is an important rule in proving the results of our paper, and it is like a building block. So the following theorem provided by Isbell, known as Isbell's exact theorem, is the most useful characterization of semigroup dominion. Basically, it gives the characterization of dominion of semigroup, which I have defined earlier. So what is that? This is the theorem. Let U be a subsemigroup of semigroup S, and let D belongs to S. And then D belongs to dominion U in S if and only if D belongs to U, or there exists a series of factorizations as follows. That is, D is equal to A0 T1 is equal to Y1 A1 T1 is equal to Y1 A2 T2 is equal to Y2 A3 T2 is equal to dot 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 so on. Ym A2M minus 1 Tm is equal to Ym A2M, where M is greater than or equal to 1 and all AIs belongs to U and YITI belongs to S. Now these are the some relations which are defined in the theorem. That is, A0 is equal to Y1 A1, A2M minus 1 Tm is equal to A2M, A2I minus 1 Ti is equal to A2I Ti plus 1. These are the relations, recurrence relations. Yi A2I is equal to Yi plus 1 A2I plus 1, and I runs from 1 to M minus 1. So such a series of factorization is called zigzagginess over U with value D, length M, and a spine A0, A1, dot, so on, A2M. So we refer to these equations as zigzag equations, and we will use these zigzag equations throughout our paper in proving the varieties to be closed in itself. Now, this is also important result up to some extent. Now, I tell the background of the paper. See, in short, I tell that all the varieties are not absolutely closed. All varieties are not absolutely closed. So from here, the idea comes into the mind when all varieties are not absolutely closed. So which varieties are closed in itself and which varieties are closed in containing varieties? Understand? Containing varieties means that, for example, this is U, this is S, and U is contained in S. So we have to see that U is closed in S or not. So in general, varieties of bands containing the varieties of rectangular band and normal band, these are not absolutely closed. And semigroup theorist Higgins had given a counterexample in his paper. Rectangular band and normal band, these are not absolutely closed. Therefore, for the varieties of semigroup, it is worthwhile to find out the largest subvarieties of variety of all semigroups in which these varieties are closed. So as a first step in this direction, one attempts to find out which varieties are closed in itself. So encouraged by this fact, Shibling has shown that the variety of normal bands are closed. So here I would like to tell the definition of band semigroup. A semigroup is called band if its every element is idempotent. That is, A square is equal to A for every A belongs to S. Band is called normal band if it satisfies the identity AXY, A is equal to AYX, A for every A, comma X, comma Y belonging to S. Now, after that, another semigroup theorist, Alam and Khan, 345, had shown that the variety of left-right regular bands and left quasi-normal bands and left-right semi-normal bands were closed in itself. And in 2, Hanger and Shah had proved stronger fact that the variety of right regular bands was closed in the variety of all bands. And recently, Abbas and myself had shown that the variety of left-right normal bands was closed in some containing homotypical varieties. What is homotypical varieties? The varieties admitting an identity containing same variables on both sides of semigroups. Now, in this section, what I say that in this paper, we have shown that the varieties of semigroup defined by the identities, same identities which I have read in abstract of the paper, are closed in itself. Now let's start. So first I have proved this lemma. This is the first step to prove variety to be closed in itself. First we prove this lemma, and we will use this lemma in proving in the main theorem. The theorem is about what? Theorem is about to prove the variety to be closed in itself. So what is this lemma? That U be a subsemigroup of semigroup S such that S satisfies an identity. S satisfies an identity AXY is equal to X to the power N AYX and AXY equal to X, or you can say that S satisfies this identity XY equal to X a to the power N by A. It means that S either satisfies this identity or this identity. In both cases, what is true? This is true. That is, and let D belongs to domain in US minus U has a zigzag of type 1 in S over U with value D of shortest possible length M, then D is this for each K is equal to 1 to M, correct? So to prove this, what we do, let me assume that the variety mu1 is the variety defined by this identity XY equal to X to the power N A by X, and mu2 be the variety variety defined by the identity axy equal to x a k power n by a with the varieties of semigroups, correct? Now we show that in both cases, whether S belongs to mu1 or S belongs to mu2, we will show that S satisfies this new identity xyz is equal to y2n minus 1 xyzy. So we have shown that in both cases, we have proved that S satisfies these identity. And now we will prove this lemma. And how we prove it? We prove it by induction. We apply induction on K. That is, we prove for K is equal to 1. We assume the result is true for K is equal to J. And finally, we prove the result is true for K equal to J plus 1. So in proving the result by induction on K, we will use the same equation. That is, this equation we will use. That is both varieties, whether S belongs to mu1 or S belongs to mu2, S satisfies same identity. So we will use this as it is shown that it is by equation 2. So in this way, we start proving this and finally we show that by induction that the result is true for K equal to J plus 1. So in this way, lemma has been established. And now finally we prove this theorem. Theorem is about what? The variety axy equal to x power n axy of semigroups is closed. That is the class of all semigroups satisfying the identity xy equal to x power n a by x is closed. Here I also want to tell this n belongs to set of natural number. It means that the same result is true for n equal to 1. That is xy equal to x a by x, xy equal to x square a by x, xy equal to x cube a by x. So this is the generalized form. That is, we prove it for n belongs to set of natural numbers. So to prove this theorem, we started from here. That is, we take any u comma s belonging to mu, and with u as a subset group of S such that D belongs to domain US minus U. Let D as a zigzag of type 1 in S over U of shortest possible length M. So what is our target? By lemma 3.1, we have written like this because it is true for M equal to 1, we have already shown. Now, finally, what we have to show, we have taken element D in domain and we show it goes in U. Once it goes in U, then domain becomes equal to U. And in this way, domain of US becomes equal to U and U is closed in S. As we know from the definition that whenever domain U in S equals to U, because domain US contains U. So we have taken an element in domain and we show it goes in U. In this way, both becomes equal to each other and variety to be closed. So while proving this, throughout this proof, we use the combination of two things. That is, we use the identity as well as zigzag equation. By using the combination of both, that is S belongs to variety, that is S satisfies same identity and zigzag equation. So by using a combination of zigzag equation and identity, we will be able to prove. So in this way, you see that S belongs to mu, zigzag equations, S belongs to mu, zigzag equations, and we will be able to prove it goes in U. So in this way, domain US is equal to U and the proof of theorem is complete. And we have proved that the variety is closed. So in a similar way, the remaining theorems we can prove. That is, in a similar way, we can prove the remaining varieties to be closed. So proving to be varieties to be closed, first we prove lemma, and then with the help of using lemma and combination of the same identity of variety and zigzag equation, we will be able to prove that domain U in S is equal to U. So in this way, we will show that varieties to be closed. So theorem 3.3, theorem 3.4, this is the lemma 3.5 we used, and we will use this lemma to prove theorem 0.6. And this is the dual part of theorem 3.7 is the dual part of theorem 3.6. So dually we can prove this theorem. So now I will pose lastly theorem 3.8b can be proved in a similar way. And now finally I pose an open problem that are these varieties considered in the paper are absolutely closed? That is, in all containing semigroups, whether it is these varieties are closed in it or not. So this is a problem. This we have to see it. All semigroup theories can see it, whether it can be solved or not. And if in the case, if it is not, then finding out largest varieties of semigroups in which these varieties are closed remains again an open problem. So finally, this is all about my paper, and these are the references. First paper is mine paper, that is I wrote myself. Ashraf. And another references are of different authors. These are all the references. Thanks for your attention.